Hi, folks, my name is Pedro Varela, and I'm here to walk you through a brief explanation and implementation about deep residual learning for image recognition. In the context of deep convolutional neural networks, it is observed that, most of the time, the deeper the network, the greater its learning capacity. Given that the issue of vanishing gradients can be addressed with batch normalization, this can be explained by considering the following thought experiment. Let's take a shallower architecture and its deeper counterpart with additional layers. There is a solution by construction for the deeper model. The added layers serve as identity mapping, and the remaining layers are copied from the learned shallower model. The existence of this constructed solution suggests that a deeper model should not produce higher training error than its shallower counterpart. However, a problem is observed. As the network depth increases, accuracy saturates and then degrades rapidly. Since this problem is not caused by overfitting, it is necessary to study and implement CNNs that overcome this issue. To address this, the authors of the paper propose the following solution. Denoting the desired underlying mapping as HX, they let the stacked nonlinear layers fit another mapping of Fx equals HX. The original mapping is then recast into Fx plus X. In other words, a shortcut connection is introduced between the input and output of every 2 or 3 layers. If the output dimensions of this step are larger than the input dimensions, projection shortcuts are used, and if they are the same, the shortcuts are identities. This is a good solution because there is no additional relevant operation for training the neural network. Below, we see an architecture of a plain neural network and its residual counterpart. Dotted lines denote the use of projection shortcuts, as the output dimensions differ from the input dimensions while the other shortcuts are identities. Now, you might be wondering, why would this work? Well, if the added layers can be constructed as identity mappings, a deeper model should have a training error no greater than its shallower counterpart. The degradation problem suggests that the solvers might have difficulties approximating identity mappings with multiple nonlinear layers. With the residual learning reformulation, if identity mappings are optimal, the solvers may simply drive the weights of the multiple nonlinear layers toward 0 to approach identity mappings. In other words, if approximating identity maps is challenging, a forced approximation to 0 is applied since the input already comes through the shortcut. Now, let's analyze if this really works. The authors of the paper trained 2 plain CNNs with 18 and 34 layers, respectively. Then, they trained a pair of Resnets with the same architecture and layers as the planes, but with the addition of residuals. It is observed that while the plane with fewer layers performed better than the plane with more layers, the Resnet with more layers outperformed as expected without the issue of identity maps. Additionally, the Resnet with 18 layers was significantly better than its plane counterpart. In conclusion, it is observed that for deep CNNs, better results are obtained with a residual architecture. We will now demonstrate how to generate predictions with the trained model of the residual neural network. Firstly, let's import the necessary pytorch modules for preprocessing, prediction, post-processing, and image visualization. We will load the pre-trained 18-layer version 0.10.0 of Resnet. While other Resnet options with more layers are available, the 18-layer version is sufficient for demonstration and quicker to load. Now, by printing the model, we can analyze its architecture. Let's start by using the image of a dog. We'll open it, resize it to 256x256, and take a look. It's a regular dog. Now, let's preprocess it. We'll crop the center of the image, returning a 224x224 image, transform it into a torch tensor, and normalize it with the same parameters used to train the model, mean and standard deviation for each color channel. Then, we can apply this function to the image and add the batch dimension, which is 1 in this case. With this, we can see that we have a batch of 1 image, 3 color channels, RGB, and the image dimension is 224x224. We can now make predictions. First, we set the model to evaluation mode, and if the GPU is available, we can direct the input in the model to it. The model's output is obtained by freezing the gradients to avoid modification. Afterward, we apply softmax to the logits to obtain probabilities. Here, we have probabilities for all classes. Next, we need a function to relate the probabilities to each category. For this, I have a text file with categories ordered according to the model's output. Therefore, we open this text file, separate the categories by lines, and use strip to remove spaces. We extract the top 5 probabilities and their respective indices with torch.top, and by looping through the top 5 probabilities, we associate them with the category and the probability value using item. Finally, we read the top 5 categories and their probabilities for the dog image. We see that the trained model has classes for the dog species and its prediction was SAMWeighted with 92.98%, which corresponds to reality. Now, let's repeat the process for the frog image. We'll load it with PIL and resize it. We see that it's a typical frog. Let's preprocess the image with the function we created, add the batch dimension, pass the parameters to the GPU, retrieve the model's output, apply softmax, and read the probabilities. We observe that the model correctly predicted the tree frog with a 96.74% probability.